stuff like that. All right, so I think we're up to schedule now that we're eliminating 2.4 completely after all the weirdness with me last week. So we're up to 2.5, so by this new schedule, we're on par. So you're never responsible for any of 2.4 for me. Okay, quiz on Friday. I think I'll just go ahead and give you the quiz that I was going to give you last Friday. So it will just be 2.1, 2.2 type of material. So as usual, I'll put you in your breakout rooms and you can talk about it, and it's not due until Monday anyway. Okay, so we're on schedule for Friday the 25th for the second exam. Okay. And the modified assignment list, so 2.2, only do the odds, 2.3, 3 to 31, skipping 2.4 altogether, so I'm ready to start 2.5. Okay. I'll go ahead and say something quickly now. From 2.7 and 2.8, they are on derivatives. Okay, now, I realize some of you have some calculus background, and you may know some derivative shortcuts. I'll go ahead and tell you, you're not allowed to use any derivative shortcuts in this chapter. Chapter 3 is all about derivative shortcuts. Okay, 2.7, 2.8, you'll be finding derivatives using the definition of the derivative, and so that's how you'll have to show them to me. If you know derivative shortcuts, you may not use any of them in 2.7 and 2.8. Okay, now some of you out there say, I have no idea what you're talking about. That's okay. That's actually what I want. I would rather that you not have any background in calculus, because then you'll be tempted to use derivative shortcuts. So I'll just say for 2.7, 2.8, if you want to use derivative shortcuts, you're not allowed to. Okay, you must do it by the limit definition, which I'll talk about shortly. Okay, the so-called derivative shortcuts are all chapter 3. Okay, and again, some of you have no idea what I'm talking about, not to worry. Okay, so 2.5, we're doing something called continuity. I introduced the concept a little bit yesterday, and now we'll do more. All right, so formal definition of a continuous function. Okay, so limit as x approaches a of f of x equals f of a. If you want to put that in your cheat sheet, you may. It's a formal definition of continuous. And what I was getting at yesterday was this. So in figure 1, we say to ourselves, is the function continuous at x equals a? It looks like it. I can draw it without lifting up my pencil from the paper. Okay? So what is it about the function that makes it continuous? Well, the function has to be defined there. Okay, that's what they're saying here. F of a has to be defined. After all, if there's no dot anywhere, it cannot be smooth, right? I have to lift up my pen to keep going. Okay. Then the other thing is that the two-sided limit must exist. The limit on both sides have to exist. And number 3, they have to equal each other. Okay. The two-sided limit has to equal to the function value, which is the whole idea that if I'm nearby, okay, when I reach smack dab at A, I don't have to jump up to get to another point, i.e. I don't have to lift up my pen from the paper. Okay. You actually don't need to know all of these for the formula, or the definition rather. It's just that. That is only the third part. Okay. That's implied in number 1 and number 2. I mean, when I write number 3, which is all that was from the definition, it implies the function exists. And it implies number 2, the limit exists. So when I write this symbol, it means the limit exists, the function exists, and they happen to be equal to each other. Okay. So that is that. Now, other things that I want to talk about. We can have continuity from the left or from the right, just like you have limit from the left and limit from the right. Okay. If you put a plus symbol, that's continuous from the right. Limit as x approaches a from the right of f of x equals f of a. And if you put a minus sign, you can have continuity from the left. Okay, and I'll show you an example of that. Okay. In figure 4 here, here's a function. Okay, we're going to say at x equals 1, the function is continuous from the left. If I come from the left side, I can actually hit that dot there, but not coming from the right. I mean, there is no graph coming from the right. At negative 1, I would say the function is continuous from the right side, because if I come from the right side, yeah, I actually reach f of -1, but that's not true from the left. I mean, there is no limit coming from the left side, right? So here's a function at x equals 1, I would say continuous from the left. At x equals -1, continuous from the right. Okay. Now, if you just want to say continuous period, then it has to be continuous from the left and the right. Okay, so let's say for this function at x equals 0, right? At x equals 0, the function is continuous from the left and also from the right. And so therefore, it's continuous right at x equals 0. Okay, I mean, that limit happens to be the same thing. All right, then on the bottom of 117, okay, it looks like a lot of memorization, not really. Okay, it says if you have two continuous functions, if you add them up, it's continuous. If you subtract, multiply, or divide them, it's still continuous, as long as you're not dividing by 0 here. And number 3, a constant times a function. If f is continuous, constant times a function is continuous. Okay, so if you have two continuous functions, if you add them, subtract them, multiply them, and divide them, you still have continuous functions as long as you're not dividing by 0. And this says if you have a continuous function and you multiply it by a constant, like multiply it by 7 or pi, it's still going to be continuous. Okay, so that's the bottom of 117. I don't think it's worth writing down, by the way. Don't write it down. And, I don't think you have to memorize it. You're just going to use it, and you're using it without knowing it in actuality. Okay. Page 118. Most of the functions that you're familiar with are continuous. Okay. Polynomials, 5x cubed minus 4x squared plus 3x minus 7. Don't write that down. Polynomial. Polynomials are continuous everywhere, okay, on all real numbers. And notice another way to write all real numbers is from negative infinity to infinity. Okay. Rational functions. What's a rational function? It's a polynomial divided by a polynomial. Okay. Fractions. They're continuous wherever it's defined. That is continuous on its domain. So you know if you have a fraction, you cannot divide by 0. But wherever the function is defined, it's going to be continuous. So rational functions, okay, p over q, where p and q are polynomials, those are continuous everywhere that they're defined. Okay. Trig functions are continuous wherever they're defined. You might recall tangent function looks like that. Okay. So wherever the tangent function is defined, it's continuous. Okay. So there's a break, there's a jump at negative pi over 2, pi over 2, 3 pi over 2, and so on. But everywhere else, the tangent function is continuous. I can draw it without lifting up my pencil and paper. And I have to pick up my pen here and continue down here. So certainly it's not continuous at negative pi over 2, but then everywhere else is continuous. And then I jump again to pi over 2 and so forth. Okay. And on page 120, you say, oh, do I have to memorize all this? Not really. I mean, most functions that you know of are smooth, continuous everywhere, right? It's only in weird circumstances where it's not. Okay, so the following functions are continuous on their domains, wherever they're defined. Polynomials, rational functions, root functions, trig functions, inverse trig functions, exponential functions, log functions, right? They were always going to be continuous wherever they were defined. Okay, so, I mean, just as a simple example, for sine and cosine, you know they look like this, right? They're continuous. You know, you don't graph it like that, and like that, and like that, and like that. There's no jumps, there's no gaps, right? They're always smooth, continuous. Exponential functions look like that. Logarithm functions look like that. Always smooth, continuous. You never graph them like that, and then like that, and then like that, right? There was never any jumps or gaps. They were always smooth and continuous everywhere that they were defined, okay, for defined values. All right, so that's that. Show it to you again. Again, I don't really think it's worth memorizing. It's like you have to come up with a pretty strange example for a function not to be continuous. Okay, and we see some examples of that. Okay, let's see. This says the limit of a continuous function. Okay, you can pass the limit inside or outside a composition of functions like this. So the limit as x approaches a of f of g of x is equal to f of the limit as x approaches a of g of x. Okay. Again, this looks more complicated than it really is. We're just going to use it, and without even your knowing it, you're going to use it. Okay. All right, let's see. 117. 117 says the limit of a continuous function. Okay, you can pass the limit inside or outside a composition of functions like this. So the limit as x approaches a of f of g of x is equal to f of the limit as x approaches a of g of x. Okay. Again, this looks more complicated than it really is. We're just going to use it, and without even your knowing it, you're going to use it. Okay. All right, let's see. If f and g are continuous, the composition is continuous. Composition f of g, the fog thing, f of g of x is also continuous. All right, and I'll get to the intermediate value theorem later. That's not until the very end of this section, so I'll come back to it. But I'm ready to start some of the problems. Okay, so 2.5. You have all of this stuff here, right? And I've kind of written it over here also at the top. Okay, so we're doing 2.5. I don't remember if I showed it to you. So for the benefit of those of you that aren't getting the book, so here's the top part of 2.5 up to 15 or so. And there's the bottom part. And then on the next page, more there. So that's up to about 32-ish. More. More. And then on the next page, next page, intermediate value theorem, 53 to 56. 53, 56, all. So there we are. Okay, that's what we got. Okay, so let's look at question number 4 now. From the graph of G, state the intervals on which G is continuous. Okay, so there's a lot of breaks there, and it might be kind of hard to see, but it goes like this. There's an open circle at -2. It shoots down there, shoots there, and it jumps down here, and a jump over here. Okay, so wherever you have a jump, wherever you have to lift up your pencil from the paper, it's not continuous. Okay, so I've got the answer here. I'm not sure I can show it to you at the same time, but I'll say it first. Okay, from -3 to -2, it's continuous. And then -2 to -1. And then from -1 to 0. And then 0 to 1. And then 1 to 3. So let me see if I can kind of go like this. Yeah, here it is. Okay, so F is continuous. I'll abbreviate with cont. From -3 to -2. Open intervals. Union, -2 to -1. It's not continuous at -1, right? Function's not even defined there. Union, -1 to 0. Continuous, continuous, continuous. Oh, not continuous at 0. Then continuous between 0 and 1. So union 0, 1. Not continuous at 1. And then from 1 to 3. So union 1, 3. Strictly speaking, not continuous at 3 because there's no graph over here. I can say continuous from the left at 3, but not continuous overall. Continuous means two-sided. And likewise, at -3, I'm going to say continuous from the right, but not continuous from the left. There's no graph over here. All right, so there's the answer to number 4. So parentheses, they're all parentheses, -3, -2, union -2, 1, union -1 to 0, union 0, 1, union 1, 3. All right, now let's see, we had to do 3 to 8 all, A-L-L, so again, I'll show you the evens, and you have the odd answers in the back. Okay, 6. Discontinuity at -1 and 4, continuous from the left at -1, continuous from the right at 4. Okay, so let me see if I can show you this. Here we are. Okay, so -1 and 4, not continuous, but continuous coming from the left side at -1. So if I come from the left side, I do reach the dot of the function at -1. And likewise, continuous from the right at x equals 4. So if I come from the right side, I do reach the dot at 4. Okay, and then the rest of the graph just jump off somewhere else like this. Okay, so this is an example. This is not the only graph. There's actually infinitely many solutions, but here's a solution. Okay, so discontinuous, not continuous, -1 and 4, but continuous from the left. So I can reach the function value at -1 coming from the left side, but not the right side. And likewise at 4, I can reach the function value if I come from the right side. So continuous from the right, but not from the left. So I jump up over here somewhere. You could also have it come down here. In fact, you could even get fancy and have that come down here, I suppose. That also works. Okay. And then number 8, neither left nor right continuous at -2, continuous only from the left at 2. Okay, so try to fold the paper again so I can show you all of that. Okay, so at -2, not continuous either from the left or from the right. So I'll just have a function value that's somewhere else. Okay, so I don't reach the function value either coming from the left or coming from the right. So neither left nor right continuous at -2. However, at x equals 2, it says continuous only from the left. So if I come from the left side, I actually reach the function value, but not coming from the right. So on the right side, I just kind of go something like that. And there we go. Okay, this is not the only possible solution. You say, how do you know where to put the y value? You don't. You just put it anywhere you want. There is no restriction. But this does seem to satisfy everything that it said there. Okay. All right, so I'll show you very quickly again. So there's 4 and 6 and 8, just so you can get it in the recording if you want to see the recording later. Okay. Okay. Number 7, I actually wasn't going to show you 7, but you have to know what it means. What's this removable discontinuity and jump discontinuity stuff? Okay. So I'm not going to show you the answer for that. You can look in the back of the book, but the language. Okay. If you have a graph like this is called a removable discontinuity. Okay. If you have a graph that goes like so, it's almost like you can pass the tire, so to speak. Okay. If I just color in the circle, now it's continuous. Okay. A jump discontinuity is like this. Okay. That means from the left side and the right side, you jump either up or down. You can jump up or you can jump down. See, for this one, there's no way you can make it continuous and stay a function. Okay. So if I can plug up here, it's still not continuous. I can plug up here, it's still not continuous. And you might say, why don't I just draw a line from here to here? Yeah, well, that would no longer be a function. It would no longer pass the vertical line test. Right? So when it's like this, you cannot possibly make the function continuous by plugging up the hole, so to speak. So this is called a removable discontinuity. Okay? You can plug up the hole. If you just color in this closed, make it a closed circle, then it's continuous. Not here. It doesn't matter if I color this one in or color this one in or put a dot anywhere. It's not going to be continuous. All right? So you figure that out for number 7. I sort of already gave you the answer, but here we go. All right. Then 17 to 23. Let me show you 17 right now. So let me make the book disappear. All right, so they're saying, why is the function discontinuous at the given a value? Okay, so f of x equals 1 over x plus 2 at a equals -2. Okay. Well, we're not even allowed to plug in -2. So why is the function discontinuous at -2? Well, it's not even defined there, right? F of -2, not defined. Okay, a little bit more about the graph. Okay, hopefully you realize and recognize what 1 over x looks like. I think this is a graph you should get somewhat comfortable with. 1 over x looks like this, what I have in green. Okay, goes like that and like that. And do you remember what happens if I replace x by x plus 2? You take the whole graph and shift it 2 to the left. Okay, so I move 2 to the left, so it looks like that and like that. And my vertical asymptote, which used to be the y-axis, which is x equals 0, now the vertical asymptote is x equals -2. Right? X equals -2. And you know you can't plug in -2. So why is the function discontinuous? It's not even defined at -2. Right? Okay, then I was going to show you 21. Okay, they got 3 pieces here. Okay, f of x is the cosine function for x is less than 0, 0 at x equals 0, and then 1 minus x squared at x greater than 0. Okay, now this one is just a single dot, 0, 0. So there we are. For x less than 0, cosine function. Okay, well, I know the cosine of 0 is 1, so I would normally draw my regular cosine function, but it's only for x less than 0. So for x less than 0, I just crudely draw my cosine function. You don't have to be that accurate. It goes something like this. And then 1 minus x squared. You should be somewhat familiar with that. Okay, let's think of the progression. You know x squared, parabola opening up, negative x squared. That reflects across the x-axis. That ends up going down. And 1 means the whole thing gets moved up 1. So 1 minus x squared only for x greater than 0 is like so. All right, so why is the function discontinuous here? Okay. The function exists. Unlike this one, when we say a equals -2, well, the function is not even defined. Here, we're asking for continuity at a equals 0. The function exists. The two-sided limit also exists. I would say the limit as x approaches 0 of the function is 1, coming from both sides. But they're not equal to each other. Right? So the limit as x approaches 0 of f of x is 1. That's not equal to f of 0. Right? So the reason why we have a discontinuity at 0 is this. Limit as x approaches 0 of f of x is not equal to f of 0. And that goes back to the definition. See if we can show that to you one more time. That was what page? 114. Okay. Function continuous if the limit as x approaches a of f of x equals f of a. But that was violated here. Okay. We do have f of 0. We have the limit as x approaches 0, but they weren't equal to each other. All right, so there we go. Okay. 23 says, how would you remove the discontinuity of f? In other words, how would you define f of 2 in order to make f continuous at 2? So they're saying there's a removable discontinuity. Okay. Where does that happen? At x equals 2, right? You can't plug in 2. You're dividing by 0, mathematical no-no. So can you plug up the hole? And the answer is yes in this case, and how would you do it? Here's all you have to do. Here's f of x, x squared minus x minus 2 over x minus 2. All you do is factor the top. So the top factors into x minus 2, x plus 1, right? Well, the 2 here means you got to have a 1 and a 2. The minus sign means you want the minus with a 2 and the plus with a 1. And notice these two cancel. So this function is the same as x plus 1 as long as x is not equal to 2. So how do I plug up the hole? Well, what do you get when you plug in 2 here? 2 plus 1 is 3. So there it is. To remove the discontinuity, let f of 2 be 3. That's all. So what is the graph of the original? So again, here's the logic. This is the same as this as long as x is not equal to 2. All right, x plus 1, graph of x plus 1, slope is 1, y-intercept is 1. It goes like that, except we know that x is not allowed to be 2. So can I plug up the hole? Is this a removable discontinuity? Yes. If I define f of 2 to be 3, I would simply plug up the hole. So this is a removable discontinuity. Now, if you have a graph that ends up jumping up to here, there's no way I can plug up the hole. That's called a that's a jump discontinuity. I would not be able to plug up the hole, so to speak. Okay. Okay, then let's see, 25 to 31, show you a couple of those. I'm going to change the directions. Let's just state the domain. Okay, so it says use theorem, blah, 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 blah. Never mind about that. We're just going to state the domain. Okay, so state the domain, never mind about the rest. Okay, they are continuous because they're rational functions and square roots and e's and cosines. They're all continuous wherever they're defined. Okay, so don't bother with that. Okay, but let's talk about domain on a couple of these. All right, so we played that game before. Okay, so 27, what's the domain of the function? Q of x is cube root of x minus 2 over x cubed minus 2. All right, so I don't have a square root, I have a cube root. Am I allowed to take the cube root of a negative number? The answer is yes. Okay, so I have no trouble spots for this. Okay, x can be positive, negative, 0. It's okay. I can take its cube root. What about the bottom? Well, I have to make sure the bottom doesn't equal 0. So I said x squared minus 2 equal to 0. Add 2. X cubed equals 2. Get rid of the cube with a cube root. Cube root both sides. X equals cube root of 2. So the domain is all real numbers except for that funny number. Okay, so domain, all real numbers minus a set consisting of the cube root of 2. It's like saying the only number you cannot plug in is cube root of 2. And you can tell what happens when you plug in a cube root of 2. Well, you have the cube root of 2 cubed, which gives me 2. And 2 minus 2 is 0. So there we go. Okay, 29 requires you to remember something about the arcsine function. And by the way, arcsine is the same as inverse sine. So they can write it like this. Same thing. Same thing, arcsine. This is less writing, but if you stop and think about it, if you have to type it on your keyboard, this is easier, right? Because you can't put that on a regular keyboard, raise up the -1, but that's easy to write. But let's say if I had to type something for you on my computer, I might just type arcsine, because that's easier as opposed to trying to get that -1 floating up there, right? All right, it turns out for arcsine, whatever's inside the parentheses has to be a number between -1 and 1. That's the definition of arcsine. Okay, arcsine has to be something between -1 and 1. So arcsine of 2 doesn't exist. Arcsine of -2 doesn't exist. And that makes sense if you recall your unit circle, right? On your unit circle, the sign of something has to be between -1 and 1, right? The circle only goes between -1 and 1. So therefore, you can only apply arcsine to stuff between -1 and 1. So that means whatever's behind my pen has to be between -1 and 1. So there we go. 1 plus 2t between -1 and 1. That's all. Then solve for t. So -1, -1, -1. -2 less than equal to 2t, less than equal to 0. Divide by 2, divide by 2, divide by 2. So -1 less than equal to t, less than equal to 0. So my domain is bracket -1, 0, bracket for this one. Okay. So what does that mean? You can plug in -1, you can plug in 0, and you can plug in anything between the two. All right, so that's that. Okay. (39) is a little bit different. How do I do 39? Show that f is continuous on -infinity to infinity. What's -infinity to infinity? That's the same thing as all real numbers, right? You go forever to the left and you go forever to the right. Okay. So they give me this piecewise defined function. Now, the only point in question is x equals 1, right? 1 minus x squared is a polynomial. We already know that's continuous everywhere. Natural log of x is continuous everywhere. The only thing which might make it discontinuous is this thing, right? The fact that it's piecewise defined. Okay. So all I have to do is see what happens basically when I plug in 1. Okay, so I'll show you how to do that now. Okay, so if it's continuous at 1, this has to be true. Limit as x approaches 1 of f of x equals f of 1. Okay, what is f of 1? Do the top one, 1 minus 1, 0. Now I need the two-sided limit. Okay, so what's the limit from the left? X approaches 1 from the left. That's the top. Less than 1. like 0.9, 0.99, and so on, I'm plugging into here. Well, we already did that. That's going to be 1 minus 0. 1 minus 1, 0. Okay, so limit as x approaches 1 from the left is 0. How about limit as x approaches 1 from the right? So if I'm approaching 1 from the right, I'm doing this function. So I'm plugging in here. So I've got ln of 1. But ln of 1 is also 0. All right, so all of these are 0. The limit as x approaches 1 from the left, the limit as x approaches 1 from the right, and the function value itself. So limit as x approaches 1 of f of x is equal to 0, which happens to be f of 1. So therefore, f is continuous everywhere. Okay, we don't need to check all the other infinitely many numbers, because for all the other numbers, right, this is fine, and this is also going to be fine, right? Okay. Now, 43 asks us something. So I'm going to show you what the wording is for 43. Find the numbers of which f is discontinuous. At which of these numbers is f continuous from the right, from the left, or neither? Sketch the graph of f. You should actually sketch the graph first. It's used to sketch first. Okay, and then you can tell whether it's discontinuous or continuous. Now, when you have a piecewise defined function like this, that's a good bet for possible discontinuities, right? I mean, you know, like x squared and x and 1 over x, they're continuous everywhere. The places where you might suspect the function is not continuous will be -1 and 1, just because they changed to a different function. Same thing for 43. So I'll do 43, you do 41. Okay, let's see, x plus 2, continuous everywhere. E to the x, continuous everywhere. 2 minus x, continuous everywhere. So the only possible points of discontinuity are where there's a change. That would be at 0 or at 1. Okay, so that's going to require the graph. So here we go with the graph. Pretend you don't know the graph. You know, I've already shown it to you, but anyway. What's the graph of that? The line, linear. Okay, slope is 1, y-intercept is 2, but it's only for x less than 0. So 0, comma 2, open circle, slope of 1 means 45-degree angle. So that's that part. Okay, then between 0 and 1, including 0 and including 1, I follow e to the x. We know that's continuous everywhere. Okay, what do you get when you plug in 0? E to the 0, which is 1. What do you get when you plug in 1? Well, e to the 1, which is e. E is about 2.7. So I just graphed it somewhere like that. So there's that middle function. Closed, closed, because you have the line underneath there and line underneath there. And then for x greater than 1, 2 minus x. That's linear, straight line. Slope of -1, y-intercept of 2. Okay, now what do you get when you plug in 1? 2 minus 1 is 1, so open circle. Slope is -1, so it falls at a 45-degree angle. All right, so there's the graph. So where's the function discontinuous? At x equals 0 and x equals 1, right? So over here, right, I don't have to lift up my pencil from the paper, so continuous, continuous, continuous. Whoop, I got to pick up my pen to come down here. So discontinuous, now continuous, 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 and whoop, again, discontinuous at 1. I have to jump down to here, and the rest of the time it's continuous. Right? So f is discontinuous at x equals 0 and x equals 1. And then it asks for one-sided continuity at these points. Okay, so let's look at x equals 0. X equals 0, it looks like it's continuous coming from the right. Because if I come from the right, I actually hit f of 0. Not so on this side. So at x equals 0, continuous, C-O-N-T is my abbreviation for continuous. You may use that abbreviation also, continuous from the right. On the other hand, how about x equals 1? X equals 1 is continuous coming from the left side. If I come from the left side, I don't have to pick up my pen to actually color in that point. But it's not continuous from the right. So x equals 1, continuous from the left. X equals 0, continuous from the right. And all other x values are continuous everywhere. Okay. All right. Okay, next one I'm going to show you is a little bit tougher. What time is it? Almost 10 minutes. Okay, so 45. The way they write it. For what value of the constant c is the function f continuous on negative infinity to infinity? Huh? What are you talking about? Okay, so this is piecewise defined. F of x equals cx squared plus 2x. If you can't read it, don't worry. I'll show it to you in a second. X is less than 2. Then x cubed minus cx if x is greater than or equal to 2. Okay, now, regardless of the value of c, this is a polynomial. This is a polynomial. So it's going to be continuous everywhere except maybe at x equals 2 because it's piecewise defined, right? So at every x value besides 2, 1, 0, -1, negative a million, positive a million, pi, e, square root of 2, it's going to be continuous. The only point in question is at x equals 2. All right, so how do you do that now? All right, so here's the function. Cx squared plus 2x, x is less than 2, x cubed minus cx, x is greater than or equal to 2. Now, in order for the function to be continuous at x equals 2, if I plug in 2 here, and I plug in 2 here, I have to get the same value. That way the limit from the left and the limit from the right will match. Okay, so all you do is you plug in 2 to both the top and the bottom and solve for c. So this says plug in x equals 2 to both the top and the bottom and set equal. That says set, and that's an equal sign. So put a 2 right there, right there, right there, and right there, and make them equal to each other. And then algebraically solve for c. Okay, so put a 2 right there. C times 2 squared plus 2 times 2 equals the bottom. Put a 2 right there. 2 cubed minus c times, put a 2 right there, c times 2. Okay, so it's not that hard. Just put a 2 there, 2 there, 2 there, 2 there. It's c times 2 squared plus 2 times 2 equals the bottom, 2 cubed minus c times 2. And now it's some easy algebra. So that's 4c plus 4 equals 2 cubed, which is 8, minus 2c. Right? So not too bad. So what happened? Add 2c to both sides and subtract 4. That's what's meant by these arrows. So this arrow means I add 2c to both sides, subtract 4 on both sides. So 6c equals 4, divide by 6. So c is equal to 4/6, which comes out to be 2/3. And that's about it for that one. Okay. And let's see, do I want to do 49? Do I have time? Yeah, I have time for 49. Make that the last one. Which of the following functions has a removable discontinuity at a? If the discontinuity is removable, find a function g that agrees with f for x not equal to a and is continuous at a. Okay, so how do you do that? Okay, so f of x equals x to the 4th minus 1 over x minus 1 at a equals 1. So it's not continuous at 1. We know that. Is it a removable discontinuity? That's the question. Okay, so I'll show you a. Maybe that's it. All right, so here's the original function. And we just do some algebra. X to the 4th minus 1 factors into x squared plus 1, x squared minus 1, right? Difference of 2 squares. You can multiply that back out, of course, x to the 4th minus 1. Now, you can't do anything with this, but you can factor x squared minus 1. Right? What is x squared minus 1? It's x plus 1, x minus 1. And lo and behold, these two guys cancel out. So we have x squared plus 1 times x plus 1, provided that a is not equal to 1, but we have a removable discontinuity. Right? So they're asking for a new function which plugs up the hole. Here's the new function. And you don't have to bother multiplying it out. I mean, you can multiply it out if you want to, but you don't have to. We have a removable discontinuity at x equals 1. That f of x equals that. Okay, what do you get when you plug in 1, by the way? 1 plus 1, 1 plus 1, 2 times 2, 4. Okay, so for this graph, 1 comma 4 is not there, okay, but you can plug it up. If you plot 1 comma 4, then that plugs up the hole, so to speak. Okay, so that's that. All right, folks, that was all I was going to do. So I'll stop share. We have maybe 5 minutes left. Let me check the chat. So yeah, when you're doing a limit problem, yes, you keep writing limit. So the problems that we had limits, you keep writing LIM, until you are finished plugging in. After you plug in, then you don't have to write anymore, as Prasanna said there. Okay, by the way, your final answer should never have limit. Okay, so when you're doing limit, right, lim, your final answer should not say lim. Okay, your final answer is 7 or 3x squared or something like that. Take off the lim in the final answer. Okay. All right, let's see. I think that's it for the chat. So anybody want to ask a question? Last 5 minutes, otherwise we're done. Anybody want? Okay, I don't hear anything, so I guess we're done. All right, so I'll continue tomorrow. Friday, at the end of class, there'll be a quiz. So as usual, I'll put you in your breakout rooms, and Prasanna and I will bounce around from breakout room to breakout room. And the quiz will be from sections 1 and 2. It's the quiz that I was going to give you last week, okay? All right, that'll do it, folks. So have a good afternoon, and we'll see everybody tomorrow. Okay, thanks. Bye, everyone.